Hello everyone. So in this module, we've been talking about the random nature of turbulence, the seemingly random behavior, and how to characterize a turbulent flow system. We realized that it is impossible to characterize with a one-time PDF, a one-time CDF. So we would need joint information, right? Joint statistics. Then in order to make matters easy, we assumed that let's say the flow is statistically stationary, meaning the statistics do not vary with time. In that case, at least there are some statistics which can completely characterize the system because it is statistically stationary with time. So covariance comes into play, autocovariance, then the frequency spectrum, correlation function, and so on. Now we looked at all of these statistics in the context of a single random variable. But as we know, the velocity field is a 3D variable. It depends on, in fact, it's a 4D variable because it depends on three dimensions in space and one dimension in time. So we have to consider a velocity vector. Now that means what we have is a random field vector rather than a random variable. So in turbulent flow, the velocity u is a time-dependent random vector field. Okay? And we'll need to use the tools that we have learned so far in order to describe this. So this we saw in last class where we would have a CDF being described as f of v, where v is the sample space vector now, f of v comma x comma t is the probability. And similarly, you would define the PDF in this fashion. So you would have small f of v semicolon x comma t being equal to the triple derivative, the third order derivative of the CDF itself. Now this semicolon here represents the fact that what we have is a density with respect to v1, v2, v3. Isn't it? This we saw last class. Now let's try to define the mean, just like we did for a random variable. Let's try to define a mean. The mean is the mean of the velocity vector. So you will have mean of each component. And so the mean would be defined as the sample space variable multiplied by the PDF and integrated over all the sample space variables. So that's how the mean is defined. The fluctuating velocity subsequently will be defined as small u is equal to capital U instantaneous minus mean. Remember, small u is the fluctuating. And all of these are vectors now. And u is the instantaneous. And u mean is obviously the mean. So what we are saying is the fluctuating is equal to instantaneous minus the instantaneous minus the mean. And this is the Reynolds decomposition of the velocity. For now, we'll deal more with that in later. But for now, just think of the fluctuating velocity as the instantaneous minus the mean. Now, if you want to think about the 1.1 time covariance of velocity, what we will have is ui uj average of that. ui uj mean, and this is the Reynolds stress, as defined as ui uj mean. These are the Reynolds stresses. We'll discuss more about Reynolds stresses in the next module. But now that we are dealing with random vector fields, and naturally since we are talking about turbulent flows, these are velocity fields which are vectors and these behave in a seemingly random fashion. Everything has to be looked at in terms of the velocity field. And that is why we have a fluctuating velocity, instantaneous velocity, and the mean velocity. Another point to note is that turbulent velocity fields are differentiable, which means if I take the mean of the time derivative, that is, the mean goes inside and what you have is the time derivative of the mean itself. Same goes for spatial derivative. If I take the mean of the spatial derivative, it is the same as the spatial derivative of the mean. So these are all, so this this can be used to determine now a 1.1 time, isn't it? In order to completely describe a velocity field, what you will ideally need is the endpoint n time joint PDF, which becomes almost impossible to determine. So theoretically, to characterize a turbulent field completely, what you need is an endpoint n time joint PDF. So with all points in space and all points in time, which is impossible to do. So in that sense, a random velocity field cannot be completely characterized. It is impossible to completely characterize a random velocity field. What we also know is that turbulent flow fields are not Gaussian. We saw that through some illustrations in the last class. And here, since a Gaussian field can be completely characterized by its mean and autocovariance, but whereas a turbulent field cannot be. So it is, and again, that also shows that a turbulent velocity field is just not Gaussian. Now let's discuss more about the statistical stationarity and the homogeneity. The random field that we are discussing here, u of x comma t, is statistically stationary if all the statistics are invariant with time. So just like what we saw for a single variable, we are now applying it to a random vector field. That's it. The definition remains the same. All the statistics are invariant in time, which means in terms of the endpoint PDF, that Fn remains unchanged if x comma t is replaced by x and t plus t, where the superscript n represents at some specific point in time, and what we are saying is, if you look at it at a later time, that PDF remains unchanged, and this is an endpoint PDF, and capital T is the time shift. Similarly, so we described what statistical stationarity is. There's also something called statistical homogeneity. So a field is statistically homogeneous if all statistics are invariant with respect to position. Statistical stationarity would be statistics invariant with respect to time. Statistical homogeneity means all the statistics are invariant with respect to a shift in position. So that means again, Fn, the PDF, the endpoint PDF, is unchanged if x comma t is replaced by x plus x and comma t. Now again, all of these are vectors. Small x is a position vector and capital X is the shift in space, which is also a vector. So if this velocity field is statistically homogeneous, then the mean field is uniform, right? The mean field is uniform, and if it is uniform, as in if it is a constant, because what we are saying is the statistics are homogeneous. It is statistically homogeneous means the means are not changing with respect to shift in position. So the mean of the velocity is a constant. In that case, you can, with an appropriate choice of frame, you can choose your frame in such a way that your mean is 0. Because if it is going to be a constant, that value doesn't matter. What matters now is only the fluctuation. So the mean velocity, if the mean velocity is uniform, with an appropriate choice of frame, you can choose the frame in such a way that the mean becomes 0. Now the definition of homogeneous turbulence is less restrictive where the fluctuating velocity field is statistically homogeneous. So here, if you have a statistically homogeneous field, if you have a fluctuating field that is statistically homogeneous, then the homogeneous turbulence becomes much less restrictive. Okay? Turbulent flows can be statistically 2D or 1D. And an example, so you might ask, where can I find a situation where the flow is statistically homogeneous? You might ask the question, where can I find a field where the flow is statistically homogeneous? And one example comes in channel flows. That's what we are talking about here. The turbulent flows can be statistically 2D or 1D. Think of an example like the channel flow shown in the figure here. For channel flows with large aspect ratios, So your B over H is much greater than 1. And your B is your transverse length. H is the distance between the two channel walls. And let's say B over H is a number that is much greater than 1. So your transverse length is much larger than the distance between the walls. And also, let's look at a situation where you are remote from the end walls. You are away from the end walls, which means x3 over B is also much less than 1. So you're not close to B. You are away from the end walls. In that case, the statistics of the flow will vary very little with the spanwise direction, as in the x3 direction, which is the spanwise direction. x1 is the flow direction here. This is the flow direction. This is the spanwise direction. And what I have here across the wall is the wall normal direction. I can call it the wall normal direction. So if I am considering a situation where my spanwise length is much greater than the wall normal length, and I am considering a point that is away from the walls, there will be much less variation, relatively speaking. So in that sense, that direction can be ignored, or variations in those directions can be ignored, which means the flow can be considered to be 2D. Now, another approximation, a further approximation can be made if you think sufficiently far down the channel. So x1 over h is much greater than 1. So sufficiently far down the channel, let's say the flow is statistically fully developed. And it is definitely possible, statistically fully developed. We are talking about means and variances. We are talking about statistics that are fully developed, not the instantaneous. The instantaneous is always going to vary because it is a turbulent flow. In that case, the velocity field is fully 1D. And the statistics will be both independent of both x1 and x3 now. So in that sense, it can be 1D. So 2D assumption can be made. You can go even further for fully developed turbulent flow. So statistically fully developed turbulent flow, and then you will have a 1D flow essentially. So that sense, you can make some assumptions. However, the turbulence itself is 3D. We are talking only about the statistics here, not the instantaneous flow variables. Keep that in mind. So we talked about statistical stationarity, we talked about statistical homogeneity. Now let's talk about isotropy. A statistically homogeneous field is by definition statistically invariant under translation. So no change, no variation with translation. So no variation with the shift in the origin of the coordinate system. You can also have the field being statistically invariant under rotations and reflections of the coordinate system. In that case, it is statistically isotropic. What do I mean by that? Invariant under rotations and reflections. That means, just as an example, I am taking u1 squared. This is the variance of the the x component of the fluctuation. The first or the x component of the fluctuation. This is the variance of that. This is equal to u2 squared equal to u3 squared. This is isotropy. So that is statistically invariant under rotations and reflections of the coordinate system. Now this concept of isotropy becomes very important in a lot of turbulent experiments, numerical experiments, numerical study of turbulence. We'll see that actually as we go in this class. Now think of this as, think of it in terms of an endpoint PDF. So the endpoint PDF Fn is unchanged if u of x comma t is replaced by u bar. So u bar, x bar comma t, where x bar and u bar denote the position and velocity in any coordinate system obtained by rotation and reflections of the coordinate axis. So that's the definition of isotropy. So now when we think of all these things, when we looked at a random variable we started by looking at the covariance, the autocovariance, and we will do the same thing here. Except you got to understand that now your autocovariance deals with multiple components. So your autocovariance is going to become a tensor. It is a vector in the sense that it depends on three components of the position vector and time, but it also depends on the multiple components, since we are considering u1, u2, u3. So the way I define the autocovariance now for a random vector field is Rij. I and j represent the different components. So I'll have u1, u2, u2, u3, u1, u3, and so on. And then now this, look at the three independent variables here. So I have r, which is again a vector, x, which is the position vector, and t is time. R is a vector, R is basically the shift when you consider the covariance. And since we are dealing with vector fields, R will obviously also be a vector. So your definition of the autocovariance in the case of a random vector field is ui uj, where ui is x comma t, uj is x plus r comma t, and the mean of that. This is also called the 2-point correlation. This can be used to find out length scales, for example. Like earlier, we wrote the autocovariance in terms of time. This is now written in terms of space. When we use the autocovariance for a random velocity, for a random variable, we determined the time scale by integrating over the autocovariance in terms of time. Whereas here, now we are just showing an example where you could derive possibly an integral length scale, L11. So we are representing it as 1, because it is obtained from the x component of the fluctuation. That's it. Only the x component of the fluctuation. We are not taking a mixed covariance. We are taking a covariance with the same component. So it is like an autocovariance in that sense. So this can be obtained by taking 1 over r11 0xt and 0 to infinity r11 e1r comma x comma t. So that would be an example where this 2-point correlation can be used. What else? The 2-point correlation will be independent of x for homogeneous turbulence, because what is the definition of homogeneous turbulence? It is statistically invariant with a shift in space. So Rij of r comma x comma t is going to be independent of x, which means it is only going to depend on r and t for homogeneous turbulence. Now, if you define a Fourier mode, this is where we are getting more into frequency analysis. We did the frequency spectrum for a single random variable. We are doing the same thing for a vector now. We are applying everything that we learned for a variable now for a vector. We are applying that to a vector. So let's define our Fourier mode as e to the I kappa dot x. So I might, while discussing these things, I might use kappa and k as back and forth. Keep in mind, kappa here is the wave number. I might refer to it as k sometimes or kappa, but I'm using the notation kappa for the wave number. So I have e to the I kappa dot x. Since your position vector is a vector, since your position vector x is a vector, your wave number is also a vector now. So when you take a vector and multiply it by another position vector, when you take the wave number vector and multiply it by a position vector, it cannot be a normal product, it has to be a dot product. So this is I e to the I kappa dot x is cosine of kappa dot x plus I sine kappa dot x. And remember, your wave number comes from, say, the wavelength itself. So if you define the wavelength as L is equal to 2 pi, which is over the magnitude of the wave number. And since the wave number is a vector, it will have a direction as well. Now, the wave number is associated with each particular direction. So just like you have the position vector x1, x2 and x3, you also have kappa vector, wave number vector as k1, k2 and k3. See, I just did that, right? I just went back and forth between k and kappa, but I mean the same thing. So that is how you define the Fourier mode. Why are we doing all that? Because we know that the energy spectrum, the frequency spectrum, and the autocovariance are Fourier transform pairs. This would apply for a random vector field as well. So now, instead of a frequency spectrum, which was for a single variable, now you have a velocity spectrum tensor, because you have multiple components and you have a vector. So you have phi ij of kappa comma t is 1 over 2 pi cube triple integral e to the minus k dot r rij of r comma t dr. You can see that I took the dot product here and I have rij, I and j because you have multiple components. And since it is homogeneous turbulence, it does not depend on x. You can see here, it only depends on r and t. This is actually a simpler life for us because we are not considering its dependence on x. So that way, if the velocity spectrum tensor is defined like that, then the autocovariance is also defined as the inverse Fourier transform of the velocity spectrum tensor. So Rij would be triple derivative minus infinity to infinity e to the ikr phi ij k comma t dk. So you would have, again, this is a triple integral. So this is 3 times integral. Why? Because you have 3 components. So your dr is dr1, dr2, dr3 and your dk is dk1, dk2, dk3. It's like a volume integral. You're integrating over the 3 components. There's a lot of information in this single variable. There's a lot of information in the single variable, and this is after making the homogeneous turbulence assumption. So if you set r is equal to 0, we did the same thing earlier when we looked at a random variable. If you set r is equal to 0, let me look at what happens when you set r is equal to 0. If you set r is equal to 0 here, now your r is equal to 0, rij of 0 comma t now becomes, by the definition of the autocovariance, isn't it? By the definition of autocovariance as shown here, if you set r is equal to 0, what you have is the Reynolds stresses. Ui, uj, and that's what you have. This is the Reynolds stresses. So the autocovariance for r is equal to 0 is the Reynolds stresses, and that by the Fourier transform definition from here, since r is equal to 0, e to the I k dot r becomes 1, and then you just have a triple integral of phi ij kappa comma t. And this is what I mean. The 2-point correlation in the spectrum contain 2 different kinds of directional information. One is the dependencies of r and phi on r and k give you the directional dependence, isn't it? Because it depends on r is a vector, and since phi depends on k, and k is also a vector, wave number vector, so you have k1, k2, k3, that gives you information about direction. Whereas the I and j, because all of these are tensors, you have phi ij, rij, so that means you will have phi 1, 2, starting from phi 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So you have a tensor. And all of these, so you have 9 components of the velocity spectrum tensor, just like you have 9 components of the autocovariance. So these different components will give you information about the different components of the velocity, u1, u2, u3, and the correlation between those components. So keep that in mind. So now we are dealing with a random vector field, which means we are talking about a lot of information in this one component. Then a useful quantity, and we did this again, I cannot repeat this enough, we did this again with a random variable where we looked at the energy spectrum. So when here also we can calculate an energy spectrum by integrating over the velocity spectrum tensor. However, the mathematics would look a lot more complicated because now you have a triple integral. Obviously you'll have a triple integral because it is a tensor, it has multiple components, and it depends on 3 wave numbers right? 3 wave number components, K1, K2, K3. So you would have, when you take the energy spectrum, keep in mind, since you have multiple components here, the energy, the kinetic energy is taken, you don't have mixed correlations, right? You're only taking U1 squared plus U2 squared plus U3 squared. That is the kinetic energy, isn't it? By definition, first principles of kinetic energy per unit mass, this is half times U1 squared plus U2 squared plus U3 squared. It is half times U1 squared plus U2 squared plus U3 squared. So it is U1 times U1 plus U2 times U2 plus U3 times U3. And that is what you're doing here. Half times, that is why you have the phi I. That is why you have the phi I. And in order to represent that, because you do not have a U1, U2. You do not have a U2, U3. You only have U1 times U1 plus U2 times U2. That is why you have the phi I. Then you have the Kronecker delta, so that you put it in there mathematically, so that you are considering only the components that are pertaining to each wave number magnitude. You are taking, so now you have your K vector is K1, K2, K3. And your magnitude is K1 squared plus K2 squared plus K3 squared, like the radius of a circle, like the radius of a sphere, I should say, because it is 3D. That is the wave number magnitude definition. So now you are taking, for every wave number magnitude, you are considering all the energy in that wave number magnitude shell. We will discuss more about this when we talk about energy spectrum, but that's what it comes down to. So for this class, I'm going to stop here, and then we will discuss more about the Ek of T and the Kronecker delta and how it comes into play. We can go further by taking the integral over the entire energy spectrum. So keep in mind, the energy spectrum itself is obtained by taking in terms of the wave number magnitude, by integrating the velocity spectrum tensor for each component separately. So phi 11 plus phi 22 plus phi 33. That gives you U1 squared plus U2 squared plus U3 squared. The Kronecker delta is to isolate, is to actually collapse all the wave numbers into a single wave number shell. And then we finally integrate over the entire energy spectrum to obtain the total kinetic energy, isn't it? So if you have the energy spectrum, and again, keep in mind, this is wave number magnitude. When I write it as K, it is wave number magnitude. So if I have a wave number spectrum like this, and if I integrate over the whole thing, what I get is the turbulent kinetic energy. I get the turbulent kinetic energy. So that is half Ui, isn't it? Half U1 squared plus U2 squared plus U3 squared. Because what we did here by taking the energy spectrum, it is still a function of the wave number magnitude. I hope this is clear. It is still a function of the wave number magnitude. In order to get the kinetic energy as one number, you will need to integrate over the entire spectrum. So keep that in mind. We'll deal, in this class, we'll deal a lot with energy spectrum, and we'll cover this in more detail later. Thank you.